Thanks, Sarah, and good morning, everyone. I am Pedro Marginelli. I'm a postdoc at the University of Washington, and let me talk a little bit about the solar system, both science and techniques that we use in this field. So just to set the stage, this is a modern-day view of the solar system. We have, in addition to the sun and the eight planets, we have three major reservoirs of small bodies. We have the asteroid belt between Mars and Jupiter. We have the Kuiper belt in the Trans-Neptunian region that starts, as the name implies, beyond Neptune. And we have the Oort clouds that extends to tens of thousands of AU, which is where most of the comets come from. So the Trans-Neptunian region, it was first postulated in the 1950s as essentially a flattened reservoir of bodies that are remnants from planetary formation. So the idea was that the objects that didn't form planets would be living in this region and would be essentially dynamically undisturbed in the 4.5 billion years since the formation of the solar system. The first Kuiper object was actually discovered in 1930. It's Pluto. It's the one shown on the left there. That's the NASA New Horizons image from its flyby in 2015. But it took only until 1992 for the second object to be discovered, is this object called Albion. And there is nothing remarkable about it, except for the fact that it was the first non-Pluto discovery. Nowadays, we know between 3,000 and 4,000 of these objects, and it's a very active field of research. The other image here is Arrokoth. Arrokoth is a representative of the small members of this region. This has a diameter of about 30 kilometers and was also visited by the New Horizons probe. Once we started discovering objects in this region, it became very clear that there was a lot more going on than what Kuiper expected. So here's a diagram of semi-major axis, which you can't see because it's being cut off, but that's okay. Eccentricity and inclination. And the key takeaway that you should get from this plot is that there's a lot going on. There are all of these sorts of dynamical effects that matter in this region. I will not talk about this in detail. If you're curious, you can come talk to me later. But the key idea here is that there's a lot of surprising structure because we have objects that are not in circular orbits. The Kuiper belt is not completely flat. And there's this region here. Let me see if I can point with this. I can't, that's fine. Oh, it's in the other screen. Never mind. There's this region here between 42 and 47 AU, which is in low inclinations, which is the cold classical Kuiper belt, and that's exactly what Kuiper thought was going to happen. But there's clearly a lot more going on. So our modern day view of the solar system starts like this. We have the planets formed in a much closer architecture that were closer to each other. There is an instability triggered by Jupiter and Saturn interacting gravitationally, and the planets start migrating to their present-day orbits. So in particular, Uranus and Neptune, they migrated outwards, and they transported the planetesimals that were closing in to the outer region of the solar system, mixing with what was already there that formed in situ, those are the cold classicals. So that's kind of our modern-day picture of how the solar system formed. So just to summarize what's going on here, we have that the TNO region was shaped by the major dynamical events of the history of the solar system. We have in addition to these large-scale changes in the orbits of the giant planets, the way the Neptune migrates completely changes what we see in the structure nowadays. We have objects that have recent interactions with Neptune, gravitational interactions with Neptune, for example, objects in mean motion resonances. So the idea is that there is an integer ratio in the period of their orbits to Neptune's orbit, or gravitational scattering. We can have the effects of things such as stars passing close to our solar system in its early history, and also maybe the possible presence of a ninth planet. So, and what does these objects look like? So I've showed this first Arrokoth image, and this is kind of a minimalist view of TNO composition and shapes. So we have that their variability is essentially associated with the way their surface looks like. A round object will be less variable than a potato, like an Arrokoth or an elliptical object. So that's basically what we see when we measure their light curves. We have that the TNO surface colors are also interesting, and they're essentially an indication of the composition of the object because we see reflected light, and TNO colors are pretty much primordial. So they will tell us essentially about where these things formed in the early solar system. We also have the TNOs can be binaries. So you have two objects orbiting each other. About 50 systems have well-determined mutual orbits, and this usually requires years of HST data because these things are very close to each other, something like separations of 0.2 arc cycles or even less. Of this 50 or so objects, 9 have wide orbits, and by wide here, I mean something that you can resolve with, say, DECAM. So it's a very very small population. So how do we observe these objects? Um, the key idea for any solar system object is that these things move on the sky. For a TNO, they're basically the most distant population. These objects move at about 5 arcseconds per hour. So here on the right are the images of the discovery of Albion in 1992. And you can see that in the span of a few hours, the object visibly moved in the images. So if you can track this motion, if you have a bunch of different images, you can build this thing that we call tracklet, which essentially tells you the rate of motion and the direction of motion. If you come back a few weeks later to observe this object, you kind of know where it's going, so you can track it and then do further follow-ups. And on the other image shows basically what these things look like over a period of a few years. These loops have exactly a period of 1 year because the Earth moves. Unlike most of astronomy, we use reflected sunlight, so the fluxes don't follow as distance squared, but rather distance to the fourth. This is complicated if you want to find much farther objects, and so you have to try a lot harder to find these things. And we have this quantity called the absolute magnitude, which is essentially a proxy for the side of the object. It's your intrinsic brightness. Let me talk about the dark energy survey now. Change gears a little bit, but it'll be related. As the name implies, this is not a survey for solar system objects. This is something made to map galaxies. I don't care about galaxies. I care about the solar system, so I have to work a lot harder than most of our members of cooperation to find our objects. So we have a 6-year coverage of 5,000 square degrees in 5 optical filters. And guess what? We have a needle in a haystack problem. I lost track yesterday. I think I saw this phrase being used 5 times, so I'm the 6th. Maybe it's more. But yeah, that's kind of the thing we're talking about here. So let me give you an overview of our discovery process. Because we want to find these moving objects, we have to use the single epoch data, so not coads like most people think of the DES data, which basically corresponds to every detection from a given exposure. We have 80,000 images with DES, so we have to find everything that is moving there. So these are these transients. From these transients, we go into pairs and then triplets. A triplet is the minimum thing, minimum number of detections that you can have once you can fit an orbit. Solar system objects require 6 parameters to describe their orbits, so that's why we need 3 detections. Then we throw that into a computer and wait for a few months and spend 20 million CPU hours until we have our set of candidates. There are things in our case, 7 or more detections that look like a real TNO orbit. And then finally, a confirmed number of objects that we do some further vetting. So the way we did this with DES is we had to first identify our transients. For reasons that are beyond this talk, our difference images were terrible. So we basically couldn't rely on them to find our moving objects. So we had to be a little bit smarter than that. So we came up with this way of doing this positional matching of all sources and individual images. So the idea here is if you know where everything was measured, you can basically do some clustering and try to figure out things that only appear once. And I ended up taking the slide out, but I actually think of this as basically the same way that Kai Tombach discovered Pluto in 1930. You're basically comparing images and trying to find things that moved. And what happens with a moving source when it's used to do a coad, if you have multiple exposures, is that your moving source gets fainter, basically because you're stacking the object with blank sky. So that's one way of spotting these things. So we started with a catalog of 10 to the 10 single epoch detections, and we were left with 10 to the 8 candidate moving objects. And to give you an idea of what these things look like in the sky, this is the DES footprint in ecliptic coordinates. And at 0 degrees of ecliptic latitude, that's where the asteroid belt is, or basically its peak density. And you can see here that once you go outside the asteroid belt, the number of detections basically drops significantly. So what this is telling you is that essentially we're doing a good job. We're finding asteroids, and that's kind of what we want to find. Asteroids are indistinguishable from TNOs at this stage. The orbit linking problem then is something that is being discussed a lot in recent years, especially in the context of LSST. So the question that we ask here is, We have 10 or so detections for a given TNO, but we don't know which detections they are. So in the sea of 100 million objects, how do we find these things? So we do this by finding triplets. And because we know how these things move in the sky, since Newton, we can use basically our knowledge of orbits to try to figure this out. So instead of doing an order and queue problem, which would be completely unfeasible with 100 million detections, we can actually have a much smaller number of triplets. So to give you a sense of scale, we started with 10 to the 8 transients, and we ended up having to fit 10 to the 12 orbits. And once again, this was a very computationally expensive task. It took us between 15 and 20 million CPU hours, and we could only target things beyond 29 AU. So that's essentially Neptune and further. To find things closer would take a lot more than that because the scaling with distance is crazy. And of course, we don't want to report all false positives to the community. So we have to do some further work to figure out what is a real thing or not. In DES, we have a lot of images of the sky, including images in, for whatever reason, weather or light curves or etc. The object is not detected. However, if we have the orbit of this object, we can actually try to see if there is some signal lying in the image, basically at a subthreshold significance. So this is exactly the idea of this test. So the red images here are the ones where we have seen the object and used it to fit its orbit. The blue images are images where there's no detection, and they are statistically independent. So if we can find some signal here, basically this means that we have a real source. And by doing this, we can compare a real object with an object that comes from a random linkage of basically asteroids and other image artifacts. And it's very clear that there is a difference. So this is a very stringent test, and we were left with a catalog of 814 objects, which puts us as 14 and short of being the largest catalog out there. And but how can we go deeper? This is all talking about single exposures. What if we want to find something at, say, magnitude 26 or 27? This is much more complicated. If you want to find a faint static source, there are basically two avenues that you can pursue. One, you can stack a bunch of images of the same spot. That's how coads are built in many surveys. Or you take longer exposures. This doesn't work for solar system objects for basically one reason. These things move on the sky. So because these objects move, if you stack your images, basically you're stacking the object with blank sky. So once again, you have the same problem with things getting fainter. Or if you take a very long exposure, your object will start to trail and you also lose signal noise that way. So the solution is this approach called shift and stack. So shift and stack is this technique where you essentially slide your images following all possible trajectories and stack them against each other. This is what this image is trying to depict here. And if you do this, once you have a correct trajectory, you will expect to see some signal. And this is what we're doing with the deep survey. The deep survey was prepared as a survey for shift and stack. We have between 90 and 100 images of each field we observed in the span of about 4 hours. And on the left there, you can see these are postage stamps from where the object was actually not detected, but seen in every image. And if you squint, you can see one or two things that look like a detection. But on the bottom, when we are actually stacking along the orbit, you can see that it's a very clear object. And to do this, we had to use as inputs difference images, and difference images comes with artifacts. So we had to come up with some clever ways of verifying our candidates. So we used the CNN as basically a real bogus identifier for objects, but it still required us to visually inspect 20,000 candidates, which is a very annoying task if you have never done that. And because we have several years of data, we can then do this process and link objects, and then we actually have an orbit and do dynamics and all sorts of interesting things. Our first multi-year sample has 110 TNOs in a very small region of the sky, something like 30 square degrees. So we are doing a very good job. So just to give you a little bit of context to what is going on here, with DES, we have basically 1/8 of the sky and 800 objects, and we are because we did a lot of analysis outside the ecliptic plane, there are all sorts of interesting objects dynamically that we've been able to find, and the objects have a mean diameter of about 150 kilometers. With deep, in this 30 or so square degrees, we have 110 objects. They are mostly cold classicals because that's exactly what we're looking for. And these objects have a mean diameter of about 50 kilometers, so it's a factor of 3 smaller. And we've only processed a sixth of the data, so you can expect a lot more deep discoveries in the next few months. So going back to this plot, the lines diagonally in the top panel are lines of constant perihelion, and 30 AU is where Neptune is. So you can see that there's a lot going on there. This is actually all the 800 objects from DES. And let me just give you a very quick overview of some of the interesting things we found. I will not enter into detail here, but we have objects in very distant resonances. These are populations that we still don't understand completely yet. We have things that usually hyperhelium, same story applies. We have things at very high inclinations. Guess what? We don't understand these objects as well. They're basically all the tails of the distributions, and we're finding with a survey like this. We also have our cold classical population, or classical population that is inconsistent with models. So there's a lot of work to be done to actually figure out what is going on in our classical population. And we have our extreme objects. Those are the ones that matter for the 0.9 hypothesis. If you're curious about that, ask me later. And I am not showing one object there. That's quite possibly the most interesting object we found. Basically, because if I plotted this in this figure, you would basically just see a bunch of dots in one place and then that thing on the other side. So there's this object called C2014 UN271. This is an orbit. This is an object with an orbit that is clearly consistent with being from the Oort cloud. So it is Oort cloud comet. And it has an absolute magnitude of 8, which puts its diameter at about 150 kilometers. This was later confirmed with thermal imaging with ALMA putting it a little bit less than that, but still very close. And so these are the images from this object at 26 AU, harder than 26 AU, and closer than 26 AU. And you can see, and this is are a very high spatial resolution, you can see the images closer to 26 AU that there's a tail that starts to develop. So we basically saw this comet turning on as it was approaching from the sun. And we measured a surface brightness of about 30 magnitudes per arcsecond squared, which, to give you a more esoteric set of units, that's 0.004 electrons per second per pixel in every image, which is very faint and very hard to find. And why is this object a big deal? Why am I talking about this thing, and why I have several slides about it? Well, first, comets are usually found distances closer than 15 AU. And typically, we see these comets at those distances because that's when they become active. They become brighter, and so they're easy to find. Before this comet was discovered, only 2 others had been seen active further than 20 AU from the sun. So it's once again on our population that there's a lot of active study on nowadays. But most importantly, comets usually have diameters less than 10 kilometers. The last time someone discovered a comet larger than 100 kilometers was in 1729. It's that image on the left there. That is a cutting edge image from the 18th century drawn by a French priest. And that's pretty much all the data that we have on that object. So yeah, we beat a 300-year-old record, yes. And then this begs the question of what other interesting active objects are hiding in survey data? This is the goal of this Active Asteroids project. This is being done by Colin Chandler. He's a postdoc at the University of Washington. And the idea is that he's feeding citizen scientists images of solar system objects taken from public DECAM data. And the task that the citizens have is to basically see if there is a tail or a coma in these objects. Once you do this with several different users and several different images of the same objects, you can go ahead and say, oh, hey, yes, this is a comet. We should take a closer look at it. And they've been able to find more than 20 objects with this technique so far. And one good thing that you can do once you do something like this is that you can start thinking about training a CNN. And that's exactly what Colin and another postdoc at UW NEMA are doing right now. They're training a CNN to try to do this automatically. So going back to TNOs, let's talk a little bit about photometry. So we have this technique called scene modeling photometry. That's basically how folks from the supernova community like to do the photometry, because it allows you to do optimal flux measurements when you have background sources. In the case of the supernova science, this is very clear because you always have a galaxy, so you have to take that out of your flux somehow. In our case, beyond doing great flux measurements, we also can do things like force photometry measurements, which are excellent for when you're trying to measure something like current amplitude. And the way this works is you have a mosaic of background sources, and basically you fit that simultaneously with your object, and that takes your contribution, your background contribution off. And you can extend this idea to fit binaries. I was telling you earlier, there are basically only 9 binaries that you can resolve with something like DECAM. Well, with this technique, we found 2 more. The idea here is that you can see along all the images of this object if there is a noticeable improvement in your chi-squared fit from having 2 point sources instead of 1. If that is the case, hey, we have a binary, we can do follow-up and analysis. Let me talk a little bit about colors. We have, with DES, we have a catalog of 814 colors, which is a factor of 8 larger than anything else in the literature, which means that we can do lots of fun things and try to figure out what's going on in TNO color space. So this is a mess. These are 814 points, uncertainties of like 0.1 magnitudes. There's no way you can do any analysis just by looking at this figure. So how can we study the structure of this parameter space? So the solution that we came up with was using Gaussian mixture models. Gaussian mixtures have been well studied in the literature. Basically, what you do is you have a clustering procedure that does things probabilistically. So you can account for things like your data uncertainties or your selection functions. And also, we modified this idea a little bit to not require the number of components to be set a priori. We don't really know how many components were there. We were trying to figure this out. So we had to come up with a way of doing this. So the way the training procedure works is we start with a very high number of components, and we basically have them fight each other. And if at some point a component is not contributing enough, we throw that away and keep going until we basically find a solution. So in other words, the resulting model will automatically tell you how many components you need to describe your data. We were left with this 2-color component model. Blue and red TNOs, I'll not talk about what this means and etc. If you're curious, we can talk about it later, but there's a lot of interesting things going on here. And one thing that I get for free when I do an analysis like this is that you can see if things fit the model or not. And it's very clear to us that not everything fits this simple 2-component picture. So basically, we're talking about finding color outliers. All these objects are at least 3 sigma from both components. So we clearly need another explanation. We expect to see 1 just from random chance, and we see 10 or so. So there's clearly something else going on. The blue objects we know come from a collisional family. There's only 1 known in the TNO region, and collisional objects are expected to have differences in colors. So, hey, that's great. We can see that. The red object is Eris. It's a dwarf planet as big as Pluto. So we also expected to see differences there. But then there are other objects that are completely different. So basically, we need to figure out what's going on there. I'll skip this slide, and I'll talk about LSST because I'm running out of time. I think everyone here has heard of LSST and is excited for it. What does it mean for the solar system? This is a figure coming from the LSST data preview 0.3 that we produced at UW. And the key idea that I should take from this figure is that the density of objects is realistic. I think we have something like 20,000 TNOs in there, simulated over 10 years. So things will get very exciting very soon. What happens when LSST turns on for us? These are predictions that are a little bit outdated. We're trying to come up with a better set of predictions. Be on the lookout for that. But for TNOs, we expect a factor of 10 increase in the total population. So that would be great. There will be a lot of more interesting objects and things to study. We know of 4 distant comets nowadays. With LSST, we should see 20, maybe. And of course, there are no planets beyond Neptune. Maybe we'll see something like that with LSST. And of course, all LSST objects will have multi-year orbits, multi-band photometry, etc. So it will be great for statistics in general. But one key idea is that LSST will not find everything. The way the LSST pipelines work is that it tries to build tracklets out of single night data. The problem we have with that is that once you have objects that move that are too far from the sun, things look static. Basically, in one night, your object doesn't move, so you can't build a tracklet. So we think that at about 150 AU, the automated pipelines will stop working. So anything beyond that will be missed. So in the bottom image here, I'm showing you distances and magnitudes. The gray area is the LSST design. The purple area is the discovery space that will be completely missed by the pipelines. And here I'm basically showing a few objects that we know of in our solar system, like Pluto and Sedna. Those things can be seen to hundreds of AU. If you have a Mars-sized planet far out in the solar system, you can see that to 500 AU or so. And Planet 9, you can see to like 1,000 AU. Of course, you can also think about shift and stack in LSST. This is much more complicated computationally than anything I've talked about here. But if it's possible, we can find something like 100,000 CNOs in our data. And that's the top panel in this figure. So that's all I had. I'll leave my summary and I'm happy to take any questions.